Okay, so now we're going to do another problem using double integration in polar coordinates. It's a problem phrased a bit differently, and you can see problems like this where it's sort of like we have to convert. So we're given a problem where we're it's set up to integrate in x and y, and then we were asked to convert, or we want to convert, or we think we should convert to polar coordinates, maybe because it's not working, maybe because it's too difficult in x and y. So this is a problem statement. Use polar coordinates to evaluate. It's kind of a funny way to say it, but evaluate the following integral by converting to polar coordinates. This is the integral. It's integral from 0 to 2 of dy it goes backwards. This should be dy dx. We're integrating y first here. I know that was wrong because these are functions of x, so the first integration is y. When I've done that integral, I have a function of x, and I integrate x from 0 to 2. Okay? But this is the statement. Y goes from x to 8 minus x squared square root. And then I have some function that has a function of x and y, and then the area element is dx dy. Okay. So right away, the question is like, do we even have any reason to think this should work in polar? And we do. The x squared plus y squared will turn to an r squared. So this thing is a simple function of r, actually. The limits are constants, okay. Here we have limits that involve some number x squared, which can actually often be a circle or a portion of that. So yeah, so far so good. It could be. If you were doing this super formally, what you try to do is you remember that, well, I mean, x equals r cos theta and y equals r sine theta, and x squared plus y squared equals r squared. In principle, you could use these things to convert everything into r and theta. But what I suggest, and the way the book even does it too, is what you would rather do is, rather than just try to stick these things in and hardcore transform it, is understand what this thing looks like and then start again and cast it from the beginning in polar coordinates. That would be what we're going to do here. Okay? Now, how do you systematically do that? So you look here. Okay? This part we will just convert by substitution. And like I said, I can already see it's 1 plus 5r squared. We'll get to that. What you do is you say, well, what are my limits? So I've got 4 limits here. I've got a bottom of x equals 0. I've got a top of x equals 2. I've got a bottom for y of y equals x. And I have a top for y of y equals the square root of 8 minus x squared. Okay? So these define the floor above which we're integrating this function. So 1 over 5 plus r squared is the thing on top. What I'm drawing over here is the floor over which we have to walk to integrate what's above us, and this is what's above us. So these are the limits of the floor. So let's just draw some lines. So x equals 0. So this is one boundary. X equals 2. This is one boundary. I'll show you in a minute. This one actually doesn't matter, but we'll see it. Okay. So that's cool. I got a vertical boundary. Everything's in between these two lines. Now, the lower limit for y is y equal x. Okay, well that's helpful. Now we're doing that. That's y equal x. It actually goes down this way as well, but we don't need that part. Okay, it's at 45 degrees. This angle is 45. And the last thing, okay, I got y as some function of x. So this here, y equals 8 minus x squared, you probably know, is a circle, right? This says that x squared plus y squared equals 8. So that's a circle of radius square root 8, or 2 root 2. So on top of this whole thing, right, we would have some circle. Okay? This here is y equals square root 8 minus x squared. Okay? So this guy here is 2. This is 2, not that matters. Okay? This is r. So it's a pie slice, right? From 45 degrees to 90 degrees, from 0 to 2. Okay? Sorry. X goes from 0 to 2. This radius is given by this. Okay, so it's a little larger. We'll see. Well, the radius is square root 8. That's the maximum here. So this distance here is the square root of 8, right? Okay. So what was a function in x and y now is simple in theta and r. It's constants. Theta goes from pi over 4 to pi over 2. R goes from 0 to square root 8. So whenever the limits of integration are constants, you should have an easy time of this. And the integration could be separable. Okay? So that's our problem now. Now let's just rephrase it and say I want the integral of 1 over 5 plus r squared over that thing. Okay, so this is what we had. Now our new integral is going to be, okay, double integral 1 over 5 plus r squared. Okay, that's just right from here by putting those two things in. Okay, and now I'm going to go r dr d theta. R goes from 0 to the square root of 8. Theta goes from pi over 4 to pi over 2. Okay? And now we've converted our integral into polar coordinates, and we can proceed. Why did I do r first? Well, because I got a function of r inside here, so that's what I'm going to do first. But like we talked about in a previous example, notice what we have here. A function purely of r, limits that are constants, so the theta integration can separate out. And it's just going to be, so this right off the bat, I'm just going to do this first. This is pi over 2 minus pi over 4 times my r integral, which is where the only work is to calculate r. So r over 5 plus r squared dr. Okay, so pi over 4 times that thing. That's what we have. And now we just have to proceed to calculate it. Okay, so our integral pi over 4. So this has that feature we talked about before. Okay, and now this is also a substitution. I'm going to let u equal 5 plus r squared. So du dr equals 2r. So r dr equals 1/2 u. So this thing is going to be equal to, well, this, here, let me just rewrite it here. No, we can do this. So this becomes r, and then I would have 1/2, 1 over u du. Right? I'm letting here u equals 5 plus r squared. So du equals 2r dr. Okay, and I make those substitutions. Okay, so this becomes pi over 8, taking the 1/2 out. I'm going to leave these as r equals square root 8. R equals 0. Oh, this is kind of silly, but okay. So that's in equal to natural logarithm. So this thing will equal pi over 8. Then we have the natural log of u, and u is 5 plus r squared at r equals square root 8, 0. Okay, so now switch the limits back to r. Okay. This becomes rate, the ln of 5 plus root 8 squared, so that's 5 plus 8, minus natural log of 5, okay, so that's pi over 8 log 13 minus log 5. At this stage in our life, we know enough to say this is pi over 8 ln 13 over 5. Don't forget, the ln A plus ln B is ln A times B. Ln A minus ln A is ln A divided by ln B. Or sorry, ln A divided by B. Okay, so very, very simple. The only big trick was at the very beginning, converting these things into the correct area. We're not integrating the area, we're integrating this function over the area. Okay? This function is easy to convert into a function of r and theta. You just input x equals r cos theta, y equals r sine theta, and you would get 1 over 5 plus r squared. You can kind of just see it. So here we just wrote r squared. If you didn't see that, you would just put x equals r cos theta, y equals r sine theta. You'd insert them in, and in general, you have a function of r and theta. Okay, cool. That's the function we're given. Then these limits tell us over what region we're supposed to integrate that thing over above. And here we had to draw them out and say, well, here's limits on x, put them on the board. Here's limits on y, okay, here's a function, draw that function. Here's a different function, draw that function. And then you have a region. Once you have that region, you can then say, okay, can I express this better in polar coordinates or not? And we found that we had a pi slice, so it was very easy to express it in just r and theta and polar coordinates. Okay, so that's also a very easy, these kind of circular wedge, like these regions over which we're integrating that are either full circles or concentric circles or part circles like pi wedges. Those are all very easy polar coordinate integrations. And on exams and stuff, that's the kind of stuff we lean into. Okay.